Minute ventilation. You know how we talked about cardiac output a lot, right? As the primary measure of cardiac function. Minute ventilation is the primary measure of respiratory function. And the reason for that is the lungs can't do anything unless they move sufficient air. So minute ventilation is the amount of air that moves by the lungs in a minute. Okay? We can calculate minute ventilation, and I can't do this on my PowerPoint. That is usually how minute ventilation is portrayed. A V with a dot over it. All right, that's minute ventilation. I just can't figure out how to make PowerPoint do that. So I just have it be MV in my notes. But minute ventilation, so you take the tidal volume times the respiratory rate. Now, tidal volume is one of those words that can mean more than one thing. Tidal volume, we refer to that as a typical breath, right? A tidal volume. It is also referred to, a tidal volume is also how much air you take in a single breath, regardless of if it's a big breath or a small breath. Okay, so think of it like this. You never breathe just once, right? You're going to breathe many, many times. The average volume of a breath over time is your tidal volume. Okay, so if we take our tidal volume, amount of air moved in a breath, times our respiratory rate, number of breaths per minute, we can get a volume per minute, right? So that's minute volume, tidal volume times respiratory rate. It's about 6 liters per minute. And its goal, it's the whole reason it is happening and why we spend energy on it, is to keep the air in the alveoli as close to the concentrations in room air as possible, right? So, you know, we're always adding CO2 and taking oxygen away from the alveoli. So if we're going to have this be sustainable, we have to keep putting new air in the alveoli and taking the old air out, right? So that's the job of minute ventilation, is to move that air around. All right, so now we have the concept of dead space. The only place in the body where gas moves, in other words, where CO2 leaves and oxygen, CO2 leaves the body and oxygen comes in, is at the alveoli and the respiratory bronchioles. In other words, the leaf end of the respiratory tree, right? You know, to use my tree analogy. Well, but in order to get air to the alveoli, we still have to pass air through the trachea and all the bronchi, right? So the air passing through the trachea and the bronchi, that has to happen in order to fill the alveoli. But the air in those spaces isn't participating in gas exchange, right? Because the air in the trachea is this great big heavy thing. There's not going to be gas exchange across that thick wall. All right, so if we consider all of the air that we move that doesn't actually go very close to blood, all right, we call that the dead space. And it's the air that we have to move to keep our alveolar air fresh, but that doesn't do any direct gas exchange. So we call that the dead space, the air moved which doesn't participate in gas exchange. All right, so it means that once we define that, the air that isn't doing us any good, essentially, we can look at the air that is doing us good, right? So if we take the dead space out of the air that we're moving, the rest is alveolar ventilation, right? So our minute alveolar ventilation is respiratory rate times tidal volume minus dead space, right? So we're going to remove the part that isn't respiratory active, and that will reduce our tidal volume by the amount of dead space that we move. Ultimately, it's alveolar ventilation that's going to determine our blood gas, right? Because the concentration of CO2 and oxygen in the alveoli is what's going to equilibrate across the blood. So dead space takes tidal volume, which is sort of the macroscopic view, and brings it more closer to the microscopic view of gases moving around. So terms. Alveolar ventilation is minute ventilation minus dead space.